Hi, my name is Meesha Kate Vicente, and in this video, I will explain the priority CPU scheduling algorithm. In this algorithm, it can either be preemptive or non-preemptive, depending on whether or not a higher priority process interrupts the current one. The basic idea is simple. The CPU always selects the process with the highest priority in the ready queue. Here's how priority scheduling algorithm works step by step. Each process is assigned a priority number. The lower the number, the higher the priority. The scheduler then looks at all the processes in the ready queue and selects the one with the highest priority. In non-preemptive priority scheduling, once a process starts, it runs until completion even if a higher priority process arrives. In preemptive priority scheduling, however, if a higher priority process arrives, it immediately interrupts the current one and takes over the CPU. The key terms to remember during this explanation are the arrival time, the burst time, priority, waiting time, and the turnaround time. Let's walk through an example with 4 processes.
We'll start with non-preemptive priority scheduling. Here we have processes P1, P2, P3, and P4 with their respective arrival times of 0, 1, 2, and 3. P1 starts at time 0 with a burst time of 5 and a priority number of 2. And if you take a look at P2 with an arrival time of 1, a burst time of 3, and a priority number of 1, we can see that P2 has a higher priority than P1. However, since this is a non-preemptive priority scheduling algorithm, P1 will run until completion before P2 takes over. P1 and P2 will have a combined completion time of 8, and by this time, P3 and P4 have already arrived at time 2 and time 3, so the arrival time no longer matters, and we will check the priority numbers. P4 has a higher priority than P3, so P4 will run until completion before P3 takes over. To calculate the waiting time, we must subtract the completion time from the arrival time and the burst time. So P1 is 5 minus 0 minus 5 equals 0. P2 is 8 minus 1 minus 3 equals 4. P3 is 22 minus 2 minus 8 equals 12. And P4 is 14 minus 3 minus 6 equals 5. To get the average waiting time, we must add up all of the waiting time from P1, P2, P3, and P4 and divide them by 4, where we get 5.25 as our average waiting time. To get the turnaround time, we must subtract the completion time from the arrival time. So P1 is 5 minus 0 equals 5. P2 is 8 minus 1 equals 7. P3 is 22 minus 2 equals 20. And P4 is 14 minus 3 equals 11. To get the average turnaround time, we will have to add up all of the turnaround time from P1 to P4 and divide them by 4, which is 10.75 in average turnaround time. Now let's move on to preemptive priority scheduling. At time 0, P1 starts executing, and at time 1, P2 arrives with a higher priority number, so it preempts P1 and takes over the CPU. P2 then runs until completion at time 4, and then the CPU is returned to P1, which finishes at time 8. Next, since P4 has a higher priority number than P3, P4 will run first until completion at time 14, and finally, P3 with a priority number of 4 runs until time 22. The calculation of the waiting time for preemptive priority scheduling is the same as in non-preemptive priority scheduling. So P1 is equal to 3, P2 is equal to 0, P3 is equal to 12, and P4 is equal to 5. To get the average waiting time, we will add 3 plus 0 plus 12 plus 5 and divide the total by 4. So the average waiting time is 5. To get the turnaround time, we will subtract the completion time from the arrival time. So P1 is equal to 8, P2 is equal to 3, and P3 is equal to 20, then P4 is equal to 11. To get the average turnaround time, we will add 8 plus 3 plus 20 plus 11 and divide the total by 4. So our average turnaround time would be 10.5.
Let's analyze priority scheduling. Its advantages include its flexibility to become preemptive or non-preemptive, its usefulness in real-time tasks where urgency matters, and how it ensures that important tasks get CPU quickly. Its disadvantages, however, include starvation where low priority process may never get CPU, how it's more complex than simpler algorithms like first come, first serve, and how it requires careful assignments of priorities. Its best use cases are in real-time operating systems and scenarios where there are different levels of urgency, like multimedia playback versus background updates. In summary, priority scheduling selects processes based on importance rather than arrival or burst time. It's powerful for real-time tasks but can cause starvation if priorities aren't managed well. Compared to round robin, which focuses on fairness, priority scheduling focuses on urgency and importance.